A huge thanks to Brian for sponsoring this video. Good morning, fellow mathematicians. Welcome back to a totally different kind of video. I have a problem to ask of you for a solution. It's not a problem which I usually state here and solve it. I have a personal problem and I want to consult the YouTube hive mind in the STEM space and maybe see if my thoughts are correct. Leave some comments down there below and help me resolve this a tiny little bit. Please watch the entire video for the whole context. Maybe it's gonna be interesting for you too. By the way, this video is sponsored by the wonderful people on Brain. They provide a great service to the STEM community and a lot of cool problems that you can actually solve. Wait till the end of the video. More information on that later. Now, as you might know, I'm doing private tutoring a lot of times during the week, multiple times, and I have this one student which is really good at school. She's a very good student and she's only doing private tutoring because she wants to get even better grades. And she's doing Abitur right now. She's in grade 11 at the moment and she got a new physics teacher. We are doing maths and physics tutoring. Now, I got a problem with this physics teacher because what they are doing right now is just waves and all of the stuff, mechanical waves, and he's just throwing stuff in and never deriving anything, just throwing stuff like Doppler effect in there without any real motivation whatsoever. And as mentioned before, she's a really good student. She's taking notes about everything. She's copying everything from the blackboard. If she's absent from school, which she almost never is, she gets the notes from her classmates. So there's not a problem with her notes at all. I am just at a real loss here. And please hear me out now. This right here is my basis for what I'm teaching at school. And then I want to do a transition over to what he does. And this is where my problems really started because I didn't know how to teach her my ways because the things that he didn't make any sense because of a lack of derivations, I think. Okay, let me now state a bunch of things. It's about the regular spring. It's a vertical spring which goes up and down. It's a harmonic oscillator. We are all familiar with this. And this right here is an exercise which I do similarly to that. And this was part of my last exam. Here it is. What my students have to do is they have to basically just fill out this diagram here intuitively, basically, with all of the energies which are part of this mass spring system. If you take a look at this right here, we have the spring which goes up and down between the points h and negative h, and 0 is exactly where we would have a stable equilibrium if we were at rest with our feather. The feather starts in an unstretched state, you could say, and only if we hang something on there, it starts wiggling around undamped. It's an undamped harmonic oscillator. And the diagram is about how all those individual energies respond to the system one at a time, depending on the position. Okay, so if we were to fill this out, I'm going to try to put the plus h, negative h here with the spring and just put the diagram here. What we have is basically this part right here. We have those three states. Now, what about the energy? I teach to my class that, classically speaking, we have a mass attached to a spring. There are three energies around. Obviously, the thing is moving, so we have some kind of kinetic energy. Obviously, our spring is going to be stretched in some kind of way during this process. So we also have a spring energy. And we also have a potential energy, obviously, because our mass is moving upwards and downwards, and hence it's just gaining some potential energy along the way or losing it. So if we were to fill out this diagram here with the energies, what is going to happen? At the highest spot up here, our spring is not stretched anymore. So there is no feather energy, no spring energy at this upper point plus h. Also, it's not moving because it's a classical turning point. It's changing that direction, so it has to brake and then accelerate once again. So the only thing that we have is potential energy, gravitational potential. Now, since we don't have the other two, our potential energy is exactly equal to our total energy of the system. So if we do this right here is our total energy. If we extend the line here, that means we have our potential energy. And if you think about the formula for the potential energy, it's just m times g times our height h or our x coordinate, wherever it is in the system. And then what we got right here is at this point, it's our maximum potential energy. And this potential energy is basically just moving linearly as a function, meaning it's going to look something like this. And at the lowest spot, obviously, once our feather is down here, if this right here is our origin of the coordinate system, we don't have any height whatsoever. And since it's a classical turning point at -h, we once again don't have any movement in there, so no kinetic energy once again. But our spring is fully stretched in its entirety, meaning overall we have a maximum spring energy. This spring energy, so this right here was our potential energy U. Our spring energy, I'm just going to call it ESP, really doesn't matter, is equal to, you can derive this by using Hooke's law. What you get is 1/2 kx². If you want to do a quick derivation, I do this in my classes. What we do as a basis, we take Hooke's law, which is nothing other than the force which acts on a spring is equal to k times x, where k is our spring constant. And if we do an integration of this thing right here, integral of kx over an interval from x1 to x2. So if we were to stretch our feather from one point to another, integrate with respect to x, what we are going to get is 1/2 kx², and all of this from x1 to x2. So overall, this x² is more so a delta x², where delta x is x2 minus x1. And if you were to integrate a force, what you're going to get is you are going to get a work done, and work is nothing other than energy, which is our spring energy. Now this thing right here is a paraboloid. If we start at the very top, so for our analysis, our spring energy is equal to total energy down here. Then at the very top, we don't have any stretching, we don't have any kinetic energy. So our spring energy is basically a paraboloid. Looks something like this. It's a bit different. And then in between, we have our kinetic energy. So this right here is U, this right here is ESP. Our kinetic energy is 0 right at the classical turning point. It's the highest in our resting position, in our stable equilibrium. So somewhere here it's the highest, but anywhere in between it's just something. They just have to fill out this diagram intuitively. So it maybe looks something like this. Really doesn't matter. Something like this. And this right here is our kinetic energy T. This is what the diagram is supposed to look like. And yeah, those right here are our energies. If we were to derive a conservation of energy law for our spring, the only thing that you would really need to do is to take yourself the acting forces and then basically integrate those forces. Now, let us do a little analysis of that because this becomes important later, and it's a little physics lesson for you out there. So what we are going to do is, at first we are going to take a look at our spring system and see which forces are going to act. So obviously we have our gravitational force acting downwards on our spring. So this is what tracks it downwards, but also our spring is gonna get stretched, meaning it wants to basically get back. It stores energy in here and it wants to get back to its original position. This right here is our force, which is going to act against our gravitational force. It's a repelling force, you could say, and this is exactly equal to Fh. This right here is Hooke's law, which tracks it back. And those two have different signs. It really depends on the choice of your coordinate system, but overall our force Fg is just the opposite of our force Fh. You see, those vector arrows, they just try to track into different directions. We have a resulting force overall. So by Newton's laws of motion, we know that just all those forces added together results in a resulting force. So we get that m times h, which is the resulting force. It's just the addition of those two, but those go in different directions, meaning overall this is just Fg minus Fh, or the other way around. If we were to write everything out, what we are going to get is, I can put it here, the diagram is gone, my picture. We are going to get that m times, and a is nothing other than the second derivative of our spatial coordinate x with respect to time. So mx double dot is equal to overall Fg is m times g, and negative Fh is negative k times x. Okay, and this is where the fun begins. This is just something that we introduced back in 8th grade at our school. We don't do differential equations at school. This is not something that we do here in Germany anymore, but this is how you would derive it, the conservation of energy for the spring system in a regular case. What we're going to do now is we're going to do some black math magic. The first thing we're going to do is we are going to multiply both sides by the velocity, which is nothing other than the change of the spatial coordinate with respect to time. So what we're going to end up with is m x double dot times x dot is equal to m times g times x dot minus k times x dot. And now I'm just going to bring everything to one side overall. So I'm going to add this term on both sides and subtract this one. What we're going to end up with is mx double dot times x dot plus kx x dot minus mx times x dot is equal to 0. Why have I done this? Think back to what I did here. What I did here is I integrated a force. So we had forces here originally, and I got work done. It's not much, but it's work. That was a great meme. We should bring it back. Now we are going to do the same thing here. We are going to integrate both sides respectively, but with the added factor of x dot, you are going to see that this right here is nothing other than the application of the chain rule basically. Now, what is this part right here? If you think outside the box a tiny bit, this right here is nothing other than the time derivative of 1/2 mx dot squared. Just think about it. If you were to differentiate this part right here, and we're just solving a differential equation, it's the same thing that we did here. It's just some black math magic fuckery that we are doing here right now. If we were to differentiate this right here with respect to time, use the chain rule. This right here is the outer derivative, drag the 2 to the front, 1/2 is going to cancel out, m times x dot times the inner derivative, and the time derivative of the velocity is nothing other than our acceleration, m times x double dot times x dot. Now, this part right here is going to be plus. We are going to take the time derivative of those out entirely. By the same logic right here, we are going to end up with 1/2 k times x squared plus, no, minus. And if we were to integrate the velocity with respect to time, what we are going to get is just the spatial dimension, so m times g times x. And all of this is equal to 0. Now here's the great argument that you find in theoretical physics. What happens if you take the derivative of a function and it's equal to 0? Well, this bit right here must be equal to a constant. This constant right here is, by definition, unit-wise speaking, an energy, just like we did here, integrating a force, resulting in work. This is an energy. This right here is an energy. This energy is constant due to the derivative term. Constant energy is the total energy of the system. Meaning what we are going to get is the total energy of our spring system is nothing other than 1/2 times m times, and the derivative of x with respect to time is the velocity squared, plus then we have 1/2 kx squared, and then minus m times g times x. And you might be familiar with all of those terms. This is nothing other than the total energy being expressed as our kinetic energy plus our spring energy, and then minus our potential energy, E pot or U. I'm going to call it E pot, potential energy, because this part right here overall is nothing other than the potential of our feather, you could say. So we could bring both of those terms together, and in classical mechanics, our total energy is always derived of a kinetic energy and a potential energy. So this right here is nothing other than T plus U, which is with respect to X. So this right here is just a classical result. And here is now finally the point where my struggle started with this other teacher, and where I couldn't really explain what to do to my very good student in the normal case, because I was just at a loss when we did our tutoring, because he did it totally different. Now what the teacher did is, and this right here is exactly what was written in her folder. What he said is that the total energy of the spring system is the kinetic energy plus 1/2 kx squared, the spring energy. This is all that he did. There seriously was just a header which said vertical spring, and then he said conservation of energy. This right here is the law. There was no derivation whatsoever. There was no clarification which kind of system we were using, which reference frame or anything of the sort. Nothing. This is what he said. And I was rightfully confused, at least I do think so, because I was seriously thinking I am teaching my students wrong at school. Is there something wrong with my equation? I don't think so. By Hooke's law, all of this works out. I derived it to you. And I was seriously at loss of words because this teacher is 54 years old. He's been in the business for almost 30 years. And he's saying that the total energy of a spring system with a mass hanging on it vertically is this right here. And I couldn't make sense of it. It didn't leave my head for 3 weeks. And yesterday I finally got an idea which also uses what I'm doing here. But if I do it like that, there's still a reference frame missing. Something is a starting point. It's just not clear. And they didn't even do any calculations with this whatsoever. The only thing they did, and this coincides with my conservation of energy, is to calculate the maximum velocity or maximum kinetic energy and also the total energy of the system once the mass is down here. And then it does work out because this is the classical turning point. And in my total energy calculation, this all boils down to just the spring energy. And obviously, since the kinetic energy is going to vanish in our turning point, this is also going to vanish. And this coincides, but he didn't do any other calculations. This is the only thing that he did. And I was just telling her, well, then just punch it into your head and just learn it, what he did there. Don't ask any questions because I can't help you here right now. Here's my idea, and I think I know where he is coming from, but without any mention of the reference frame or anything of that sort, it just isn't good to teach this to students, and I think it's just plain wrong whatsoever. And it boils down basically to this right here. This right here is missing. Let us start with our total energy of the system that I derived to you a second ago. So once again, I'm going to write everything out. The total energy is nothing other but our kinetic energy plus, and what we are going to have is 1/2 kx squared minus m times g times x. And it really doesn't matter if the potential energy is positive or negative because it really just depends on the reference frame and if your gravitational force is acting upwards or downwards. It really doesn't change anything in the grand scheme of things. Here in Germany, I teach it to my students with a positive sign. So if you're confused by that, it really doesn't matter. It just has to do with this relationship right here, and that the gravitational potential is just the negative integral of the gravitational force. So if you choose your force acting downwards, the negative and negative becomes positive, and you get a positive sign right here. Now, let us go ahead and get started. What I thought is, in order for us to trace all of this back to just this energy of the spring, is I'm going to complete the square, because we basically have a square term here. And what we could do is we could take a look at another scenario, namely if our spring comes to a halt. If our spring were to basically stop in its stable equilibrium position because of damping and the like, then we have our equilibrium point where it holds that Fh is equal to Fg. If those two forces are equal, then our mass is gonna stop. It's gonna be just standing there without any movement whatsoever. And then we have an equilibrium position where it's not trying to move anymore. If we take a look at this as our starting point, Fh is equal to Fg, then this turns into k times x is equal to m times g. Or if we were to reformulate this, then the equilibrium position is equal to m times g divided by k. And maybe you can already see where this is going. If we were to use this change of variable right here, then we are going to end up with. And what I'm going to do is I want to complete the square. I'm going to factor out 1/2 k on both terms. So 1/2 k times, now we get x squared minus. If we factor out 1/2 k, we need a factor of 2 times m times g divided by k here times x. Now you might see something. M times g times k is nothing other than our equilibrium position of our harmonic oscillator. Now this thing right here is nothing other than x equilibrium. And this right here is nearly a binomial formula. The only thing that's missing is this x equilibrium squared term. So we are going to add it. And we can just add it. We'll also need to subtract it in order for us to get an equivalent statement. So negative x times eq squared once again. Now this part right here is just a binomial formula. It's going to end us up with t plus 1/2 k times. This is x minus x equilibrium, but squared, and then negative x equilibrium squared. Now if we were to just multiply everything out now, we are going to get a total energy of t plus, and now we have 1/2 k times x minus x equilibrium squared minus 1/2 k x equilibrium squared. This right here is a spring force exactly at our position x equilibrium. If you were to set your coordinate system in such a way that we don't have any difference in stretching, basically, this term not right here. So if our spring isn't stretched at this point, basically, then this energy right here is gonna vanish because we don't have a stretched feather, and hence we don't have this energy term which is constant. Or in differential equation terms, we can just add it on both sides and absorb it in our total energy. So if this right here were to vanish by choosing our coordinate system accordingly, then this part right here would be exactly what he is saying. This right here turns into t plus 1/2 k times delta x squared, which is exactly the work done on a spring. But this only works if you specify some kind of starting point in your coordinate system or a certain reference frame. But this is exactly where my problem was. I couldn't help her. And maybe you can tell me down there in the comments below what your inputs are regarding this matter. This is what I got, and this coincides with this formula, and you probably find something like this too online or anything of that sort. It's probably something that you find in a higher physics book or in some theoretical physics lecture, but it's not suited, in my opinion, for students grade 11 and upwards. It's just not is, because this speaks against everything that they have learned before, because there is no involvement of the classical gravitational potential, which is acting on our mass. So either I am totally wrong with what I'm teaching, and if I am, please tell me down in the comments such that I can change my ways, or this teacher right here really just has done goofed, and I should just forget about it because she's already done with her exam and she's never gonna hear about this ever again in her life. But this seriously bugged me for 3 weeks straight, and I think I found a solution, and please tell me down there in the comments below what you think. And if you want to see more problems, if you are really excited to do more STEM stuff, then the contents of today's sponsor, Brilliant, might be the perfect fit for you. Now, when it comes to theoretical physics, visualizations are key. There's no way you could get through any theoretical physics or physics course in general without doing some kind of visualization. Be it only just the sine wave which dictates how our spring is moving. It doesn't matter. Without any graphics, you are actually cooked in physics. And this is where Brilliant comes in totally clutch. Brilliant are masters at educating others. With their over 70 interactive courses in all topics STEM, be it the mathematics that we did today, physics, computer sciences, chemistry. They provide you with the greatest library, at least in my opinion, of STEM-related courses online. They actually doubled their courses in 2025 and give you even more room to play with, more courses that you play around with. And the best thing about Brilliant is that they personalize your courses and they give you personalized practice sets. So depending on your background or where you are at your studies, they actually make it easier for you to get started over there, and to provide you courses with the right difficulties and also practice sessions. They are just very good at what they do, and their team of animators are absolutely geniuses. They are totally brilliant, pun absolutely intended here, and they really know what they are doing. Just take a look at anything of the stuff that I show you on the screen right now. Doesn't this look wonderful? It's colorful, it works out smoothly, you can play around with all of this stuff, it's extremely interactive, and it just makes learning so much fun. Brilliant is not only a website and app, no, Brilliant is a movement inside the STEM community which helps worldwide students to get better at STEM on a daily basis. And if you want to be part of the STEM movement, then definitely make sure to use my linky down there at the top of the description, brilliant.org/flammymaths, or my QR code somewhere up here in the corner. With it, you are going to get free access to the entire landscape of Brilliant. But if you feel like you want to access more, you want to get the full portion of Brilliant and even more stuff, updates, Christmas presents and the like, whatever, then definitely make sure to use my link in its entirety and get 20% of an annual subscription. During Christmas, they do a lot of stuff. They add extra courses, extra practice sessions and the like, and they just do cool stuff, and they also do some graphical overlays and the like. It's just cool to look at. Definitely make sure to check it out, and maybe this could also become a Christmas present for a loved one of yours that actually enjoys STEM stuff. So check it out, support the channel this way, and I thank you guys for watching. I hope you did enjoy this video, and maybe you can help out down there in the comments below. And up until the next video, I'm wishing you guys a phenomenal day. See you.